Today we're going to talk about different compounding intervals. And the first thing we're going to look at is return over the years. So earlier you learned about a bank account that had an initial balance of $1,000 and earned 1% monthly interest. Each month the interest was added to the account and no other deposits or withdrawals were made. So to calculate the account balance in dollars after 3 years, Elena wrote 1,000 times 1.01 to the 36th, and Tyler wrote 1,000 times 1.01 to the 12th, or to the third power. And we want to know, why do Elena's expression and Tyler's expressions both represent the account balance correctly? So with this, your initial balance is $1,000 and it is 1% monthly. So we do need to move that decimal place twice. We're getting 1.01 for our B value. Now think about it. It does say 3 years here. So how many months happened? Since it's a monthly interest, we do need our exponent to be in months. So how many months happened in 3 years? So that's 36. So that's where Elena got her exponent. Here, Tyler took this rate to the 12th power for 12 months, and then took that to the third power for the 3 years. So do they equal the same thing? Well, yeah, when you plug them in, they're going to both give you $1,430.77. Exponent rules tell us that this is also a valid method, because an exponent to an exponent means we multiply those two things together. Kieran said that the account balance is 1,000 times 1.1268 to the third power. Do you agree? Why or why not? If you plug this into the calculator, it's not going to give you this same amount. So if we do that really fast here, we take 1,000 times 1.1268 to the third power. It doesn't give you the exact same amount. It's close, but not exactly there. So why is that the case? Well, if we're looking back at Tyler's information here, if we take 1.01 to the 12th power, we use order of operations to do that first. That's the 1.1268 okay? And so then if you take that entire decimal, there's obviously more decimals after that. If you take that amount and plug it in, so if we do 1.01 to the 12th power, okay, and we take 1,000 times that answer to the third power, we are getting the exact same amount that Elena and Tyler got. So it is true that they agree. This right here is what we call the effective interest rate, what's actually happening in practice. All right, so changes over the years. The function f defined by f of x equals 15 times 1.07 to the x models the cost of tuition in thousands of dollars at a local college x years since 2017. So what is the cost in 2017? This is our beginning balance. Since it is in thousands, it's going to be $15,000. At what annual percentage rate does the tuition grow? Well, remember, for rate, we're looking at that 1.07, the B value. That is 1 plus, since it was interest. And if you're just getting rid of the 1, you have 0.07. We move that decimal place 2 spaces back over. We have 7% tuition growth. Assume that before 2017, the tuition had also been growing at the same rate as after 2017. What was the tuition in 2000? So with this, if we're in 2017 for our thing here, but our question's asking us 2000, we need to go backwards in time, which means that we would be at an x value of negative 17. And when you plug that in, you get an answer of this. But this should be in thousands, so we're going to take that answer and multiply it by 1,000, and we get $4,748.62 for tuition in 2000. So then what was the tuition in 2010? Well, again, we're going back to that same starting value of 2017, so we need to go backwards in time 7 years. When we plug that in, we get $9,341.25. Again, you're getting this answer. You have to multiply it by 1,000 since it's in thousands. What will the tuition be when you graduate from high school? So if we're talking about 2017, then you would graduate high school 6 years after that. So you multiply it in, and then you're going to multiply that by 1,000. Tuition would cost $22,510.96. Okay? Now, it says between 2000 and 2010, the tuition nearly doubled. So from 2000 to 2010, it almost doubled. By what factor will the tuition grow between 2017 and 2027? Okay, there's a 10-year period there happening. So we would also take 1.07 to the 10th power. Okay. Choose another 10-year period and find the factor by which the tuition grows there. So if we're going from 2022 to 2032, we're going to take that answer from 2022, multiply it by another 1.7, and do that every single year until we get to 2032. So it would be 1.07 to the 10th power. Again, what can you say about how the tuition changes over any 10-year period? And this is assuming that the function f still represents to be and is an accurate model. So if we're going another 10 years from anything, we're going to still have 1.07 to the 10th because you multiply 1.7 10 times for the 10 years that the changes have happened. Okay? All right, so here, which one we would choose? Let's talk about the situation first. So we have $500 to invest. We have two investment options. So say it's a bank is going to offer us every 3 months 3% interest, or we can have every 4 months 4% interest calculated. And we want to know which option we would choose. Okay, and let's focus just on 1 year. In 1 year's time, what would I want? Okay, so for this, option 1, we would take our initial balance of $500. It is 3%, so we would move that over and get 1.03. And if we're compounding interest every 3 months, that happens 4 times a year, so we would have $562.75. For option 2, we have that again, initial balance of $500. Since it's 4%, it's 1.04. And it's to the third power because we are only getting interest accrued 3 times since it's every 4 months. So we would want to choose option 1 because it calculates more often. Right now we're not getting too much more money, but as the years progress, you would eventually get more on those original investments. Could there be certain months or years that it would happen that option 2? Yeah, but most of the time, option 1 is going to be your better option because it calculates it more often. All right, talking about credit cards. So a credit card company lists a nominal APR or annual percentage rate of 24%, but compounds interest monthly. So it calculates 2% per month. They give you an annual percentage rate, but if they compound it monthly, you have to take that rate and divide it by how often you're calculating it to get the percentage rate per time that you're calculating interest. Okay, so we have a cardholder who made $1,000 worth of purchases using his credit card and made no payments or other purchases right now. And then we're going to assume that the credit card company does not charge any additional fees other than the interest. So if you have a late payment, they're not charging you extra. So we want to write expressions for the balance of the card after 1, 2, 6 months, and a year. So those would look like this because, again, we have our starting balance, our 2% per month. We're going to move that over twice and get 1.02 after 1 month, 2 months, 6 months. And since we're calculating it monthly, we do need to have this in months of 12 months. It says just write expressions so we don't have to actually calculate those things out. Okay, so what happens if we want an expression for the balance in dollars after M months without payment? So here we're just making that M be for months, whatever it was before. How much does the cardholder owe after 1 year without payment? So if you actually type this into a calculator, you actually calculate this, they're going to owe $1,268.24. So what is the effective APR on this credit card? If you take that interest, divide it by the original investment, and then make that calculation, again, we're going to turn this into a percent by moving the decimal 2 spaces, we get 26.8%. We want to write an expression for the balance on the card in dollars after T years without payment. Okay, so if we don't make any sort of payment on this, it is after T years, so we need to multiply that T by 12. So if it was 2 years, it would be 24 that you're using as your exponent, and so forth and so on, depending on your years. Okay. All right, so last thing here, sorry. Are you ready for more? So a bank account has an annual interest rate of 12% and an initial balance of $800. Any earned interest is added to the account, but no other deposits or withdrawals are made. So we want to write an expression for the account balance for different situations. So if after 5 years, if the interest is compounded n times per year. So you notice up here, I didn't say b equals 1 plus 0 or 0.12 to get 1.12 because I didn't know how often it was being calculated. So we're 5 years, we're being compounded n times per year. Remember earlier when we had that interest rate of 24% annually, to get it monthly, we divided it by 12. Okay, so keep that in mind here. Here, we don't know exactly how many times it's being calculated for the year, but we will take 1 and add to it that 12% divided by the number of times that we actually calculate the interest. Okay, that would give us some sort of number that we're going to take to the 5n power. Why is it 5n? Well, we need to multiply 5 years by n number of times that it's being calculated. When it was 12, or when it was monthly up above, then we took the number of years and multiplied it by 12. Okay, so it's going to depend on how often you're calculating that interest. So after T years then, if the interest is compounded n times per year. So now we don't know how many years it is, but we don't know how many times we're compounding it, but we still know that we started with $800 and that our annual interest rate is 12%. So there we have 800 times 1 plus the interest rate of 12 divided by the number of times we're compounding it for the year, all to the number of times we're compounding it times the years that we have. Okay? So we're going to look at one more here with that. What happens if we don't even know what the initial investment is? So after T years, we have an initial investment of P dollars and an annual interest rate of R compounded n times. So we don't know anything about this. We're just saying in general. We would take our initial amount, multiply it by 1 plus the annual percentage rate divided by the number of times you're compounding the interest to the number of times you're compounding interest times the number of years in this. So the only time you have to do this is if you are given an annual percentage rate and you are compounding it a different amount of time besides years.